is a table. So the goal of the meeting today is to get an algorithm that will help us to fill this table. So this table will be an analog of what computer is doing when optimizing geometry. This will be an oversimplified example. As we go from one row to another, we will get to more and more precise geometry. So basically, we need to fill all cells into this table. And in class, we'll do maybe one cell per person. At home, you fill table with slightly different initial parameters once again on your own. And we will return to the table in whatever 30, 40 minutes. Right now, I'm going to the slides, and we will get enough information to complete this subject. Okay. So we are in computational chemistry class. Our goal is to watch how the background theory and equations are implemented in software on hardware, where we take molecular models, compute their properties, and compare them with experiment. Yesterday, we did an important step compared to a week ago. A week ago, we did split molecular Schrodinger equation onto electronic and nuclear part, onto electronic Schrodinger equation and nuclear Schrodinger equation. And yesterday, we replaced time independent nuclear Schrodinger equation to time dependent Schrodinger equation. And then decided that we focus only on the expectation value of positions of ions. And when we carefully do it, it relates to Heisenberg equation of motion and Ehrenfest theorem. We are getting equations which are very, very similar to Newton's equation of motion. The only difference that instead of electrostatic repulsion of nuclei, there is additional term to nuclei interaction that is borrowed from the electronic part. So from now on, we do have Schrodinger equation for electronic part and Newton's equation of motion for positions of nuclei. Now, we do need to set up an algorithm to for getting an idea what computer is doing when we optimize geometry. So when we met in the lab, we all were drawing molecules, right? And in your homework, you were clicking on a screen, getting spheres connected to another spheres and telling this is molecular or atomistic model of a molecule. By looking on your own work and maybe those examples that I did show yesterday, screenshots, you see that humans may draw something that is interesting but not ideal. And there are interatomic distances, angles, and dihedral angles. There are configurations that are more appropriate for a specific set of atoms, for specific nuclei. And the distances and all structural parameters that provide minimal energy, that bring system closer to the global minimum of the potential energy surface, is referred to as geometry optimization. Last Wednesday, we did a broomstick, right? Which is not a true optimization. It's just a like quick help tool. But maybe tomorrow we will already start doing actual optimization when the job is submitted and there are specific algorithms to find the minimum, and we need to get an idea how it works. Some of you are practicing it every day, especially if you are in force field materials design. Some of you may be aware of this like steepest descent and conjugated gradient, but we are going to just briefly overview. And our main goal is to bring this idea into algorithmic way and see that a minimum can be found in a way of following precise steps. So basically, all activities that we are going to overview in today's class are shown on this slide. So we take expectation value of derivative of potential energy over elongation of ions, which sometimes is referred to as gradient. And the gradient of potential is force. Force shows us where atoms need to move. So we change positions of ions according to the direction of the force, and then we recompute an increment in positions. So this increment of positions is feedback into new point on the potential energy surface, and then the procedure is repeated. So basically, there will be no more ideas. I will repeat the same idea again and again from different, looking on different angle. But right now, I wouldn't be surprised if some of you or several of you raise hand and ask, wait, why we are doing it? If we know potential energy surface, we can just order all data points and find which one is minimal, right? Raise hands if you had this idea. Raise hand if you have had some suspicion, but you didn't know how to express it. Bring everyone to the screen. Okay, so okay, I appreciate your trust to what I'm saying, but feel free to develop some critical, how to say, suspicion. So one of the reasons, one of the specific feature of what we are doing, which is different from the force field software, that potential energy surfaces are unknown. Forces between pairs of atoms are not tabulated. In what we are doing, in some sense, we are doing a silly job. As soon as we move configuration, as we change position of any individual atom, we need to recompute electronic structure. We need to find, I'm going to flip back a couple of slides. So we need to resolve again electronic part, which will be different. This V sub En does depend on positions of ions. The eigenenergy does depend on the position of ions, and this eigenenergy contributes to the potential energy surface. So anytime we move ions, we recompute electronic part. This is this can be replaced by force field approach if we have a guarantee that our model is intact and there is no bond breaking. If we just have maybe just looking for isomers, looking for physisorption of molecules on the surface, looking on maybe elasticity of materials. But as soon as any trace of chemical reaction may pop up, as any bond may break or form, we need to do whatever we are doing right now to recompute electronic structure for each position of ions. Okay. So I think this is in previous year at this point we were doing a little interview, and I probably was asking class attendees to go to the board and derive a couple of equations. But let's do it quicker right now. So we do have set of classical equations for for expectation value of positions of ions. It is more healthier if we treat coupled equations for position and for momentum, as we did yesterday. And then as soon as these equations are set up, one may go forward and solve it. So the equations that we need to solve include the derivative over time of like position and momentum, and derivative over space for potential energy. So if we need to find a solution of Newton's equation of motion, what do? Anyone wants to briefly summarize how we typically solve Newton's equation of motion? Like put thumb up if you volunteer, put thumb up if you fear and do not know what to answer, and put in the middle if you heard about it but you prefer not to speak if it is not critically necessary. Okay. Okay. Hanmant, middle, Sayed, Amir, Sarah. Okay. Let me try Amir. Please, I think we can spend a few minutes. Please unmute your microphone and just briefly tell how you are typically solving Newton's equation of motion.
So basically, we're trying. Let me see. So which one is the actual equation here? So
the actual equation is written in the red color, and then with the blue color, I was trying to write the procedure of solution. So second derivative, Newton's equation of motion is force equals mass times acceleration, right? And acceleration is second derivative of position, right?
Sure, yeah.
So we can write it down as acceleration equals force divided by mass. So the goal is to find position as function of time. What do?
So we calculate the integral of it, first of all.
How many integrals?
I believe it's going to be 2 integrals because it's the second degree derivative of momentum.
Okay, yes. So just by integrating left and right part 2 times over time, one is going to get the solution for position, how position changes over time. Hadassah, do you confirm? Okay. So this way to solve, thank you, Amir. This equation would be, this way of solution offered by Amir will be absolutely correct, and we would not need anything if potential energy surface and force unknown are available. And it is what we were doing in high school when solving a problem of mass falling down in gravitational force, right? So or like oscillator, when the force is proportional to elongation or to position, or force is constant, then this equation is easily solvable. But as we were discussing on the previous slide very recently, The whole challenge of this activity that we may not know, or more typically, we do not know what will be the force in the new position. So we need to make a little step and then recompute force. So we will use the solutions that Amir has suggested, but we will apply it to infinitesimal small steps. Make solution, make step, then recompute force, then make another solution. And then we will do step by step, exploring either molecular dynamics or geometry optimization. So if we integrate, wait, just a second. So is it? So if we integrate for the first time, we are reducing the order of derivative from the second derivative to the first one. And we are getting the integration constant, correct? Okay, and on the left part, and on the right part, we are keeping this gradient of potential multiplied by time increment, because integration over time of a constant is just linear. So now we need to integrate the second row. Hadassah, would you please unmute microphone and help? How do we proceed further from the second line to the third?
I mean, I guess my first thought would be integration, but I'm trying to see, integrate again, but I'm trying to see if there's something different you do since there's the DUDR, which
So,
still folds the next line.
Yeah, so if we integrate the first derivative of the first order, we are getting the function. We bring function to the way without derivative, right? Right?
Yeah.
So instead of dr over dt, we have r as function of t. The constant from our previous integration yielding a factor times t, right? And we
Yes.
get another second constant for the second integration. And on the right part, we integrate the gradient times t, which originated from first integration, and then integral of t will be t squared over 2, right? Approve? And then, yeah, thank you. And then we will collect r of t on the left side and everything else on the right side. So it will be constant 2, constant 1 times t, and the gradient times t squared over 2. So it looks very much to the solution that most of us were getting in either high or middle school when looking for the free falling object, right? So C2 is initial position, C1 is initial velocity, and du over dr is a free fall acceleration, right? Agree? Or repeat? So C2 is initial position, C1 is initial velocity, and du over dr is free fall acceleration. If we are just throwing stones in the gravitational force, or if we are sending projectile with a catapult in ancient Rome, or if we do modern artillery, or if you launch the space rocket, they all just evolve in gravitational force. Okay. In our approach, we will not use t going to infinitely long time. We will use it only for infinitely short time, because u potential and du over dr force will be recomputed, will be changed at each time we increment the position. So the position at time t1 plus delta t will be position at time t1 plus the dr over dt, which is velocity at time t times increment of time. Then this gradient derivative of potential over position computed at old point r of t1 multiplied by time increment square over 2. So the same thing as before, we just give names to these constants. And one can prove this statement just by making things equal to each other at given time. So those of you, I just know that a lot of research groups in civic engineering are doing materials designed by force field. So if you are in those groups, you are just solving this equation and practicing this solution. Here we are going to, our difference of this course from force field, that U, potential energy surface is recomputed based on electronic structure. Okay. So we do want to implement this solution into algorithm. We want to, in the remaining, whatever, 25 minutes, we are going to do two things. First thing, we are going to pretend that we are programmers who write codes for computers and for robots. And then we will pretend that we are robots. So each of us is a little computer who is trying to follow this program, this algorithm. So we are converting the solution of Newton's equation of motion into discrete algorithmic way. So to do it, we need to, we are going, instead of continuous time, we are going to make discrete time, go step by increments. Then for gradient, for the force, we need to introduce a rigorous definition. So if our time is discrete, then positions will be also discrete, and then forces, the derivative of the potential over increment of position can be defined as potential for position at time t plus delta t, so future position, minus potential at present position u of r of t. Sorry, the part of screen is not visible. Divided by increment of the position r of t plus delta t minus r of t. So this is typically the first equation in the calculus course. This is just definition of the derivative of infinite differences. So I think everyone should be fine with this equation, right? Let me just quickly make sure that everyone is happy with this definition. Okay, yeah, thank you for the support. So we have the force infinite differences. Then we are, instead of using the prediction of the position at next time, we need the increment in the position. And then we need to take this r of t back to the left side. So we need to subtract r of t plus delta t minus r of t. And it will be equal to this velocity over mass times delta t and this gradient over delta t squared. Right now, we are going to neglect inertia. We are going to neglect momentum and assume that there is a dampening factor that brings any velocity to zero instantaneously. This is a trick to help simplest way to arrive to a minimum. So we are going to mimic to model arrival to the minimum of potential energy surface. So I'm putting a little red cross here. But later on, by the end of the course, we will return to molecular dynamics, and then we will use the inertia. Also, there is a thing that is not standard and we cannot derive it, but it is a trick. We are going to, instead of using true force, we are going to use a little smaller force. We are going to use dampening parameter between 0 and 1. And this trick also helps to arrive to correct solution quicker. Without this trick, one just put gamma equals 1 and everything will be like literally correct. But making it a little smaller will help. So I'm a little less organized this semester, but in previous semesters, I was given another homework asking all class attendees to summarize the definition of potential energy surface and provide a figure from the internet illustrating what potential energy surface is. And here is the key to such homework. So potential energy surface may have global minimum, local minima, transition states, and the goal of optimization is to find global minimum. As a little comment, if system falls down into local minimum, one needs to either hit and do simulated annealing or to practice Monte Carlo. But it's a little away from our course. So we're just trying to arrive to global minimum by optimization, assuming that we are already near it. We just need to find the overall point. If there is no minimum, then it is a dissociation, so it is typically for combustion and explosion. But right now we are assuming that system has a stable minimum. So a little comment that I was expecting that someone may suspect that we are doing something wrong and criticize the content of this class right away. So suppose we do have knowledge about potential energy surface for all discrete points. Suppose we have, like, I don't know, 1, 2, 3, several degrees of freedom. Each degree of freedom we discretize onto grid points spaced away from each other. And for each multidimensional grid point, we already know the value of potential energy surface. Then we do not need any algorithm. We just plug in this multi-variable function into Excel and tell, like, order it, find the minimum, right? And then we will find what is the value of minimum and what are the positions that are responsible for this minimum, correct? So if this will be true, then our whole lecture is garbage. But by some reason, I'm repeating this lecture from year to year. So there should be a trick. There should be a reason for it. And exactly, right. So if we do have, suppose each degree of freedom is discretized only on 10 grid points, then for diatomic molecule with 1 degree of freedom, we will have 10 grid points, which we can do on Excel. Then for triatomic, like for water molecule, there are 3 atoms, and number of degrees of freedom is counted as 3 times number of atoms minus 3 translational minus 3 rotational will be 3. So if you have 3 independent degrees of freedom, then total number of grid points will be grid points per 1 degree of freedom to the power of number of grid points. So like 1,000 grid points. It's also easily doable by Excel, right? Now, if you have 4 atoms, so 3n minus 6 will be 6. 10 to the 6 million points. It's also quite doable in PC. So acetylene, if we are up to acetylene molecule, we can do optimization of geometry without any specialized software. But if we just go to a simplest alcohol, it's not drinkable. Methanol is poison. CH3OH, so 6. Is it 6? Right, 6 atoms. So 6 times 3 will be 18. 18 minus 6 will be 12. And then we have 10 to the power 12 is still okay. It's whatever, terabyte of data. It's still doable, but maybe not comfortable. But anything with that will have bigger than 6 atoms will overwhelm the memory of our computers and needs an algorithm how to go from point to point. So even if we do have a pre-computed table of the potential energy surface, so browsing in the space locally, browsing from by local infinitesimal changes, increments, is still most optimal way of optimization. Okay. So if it is more than 1 degree of freedom, gradient is multidimensional. Our goal is to find minimum of a function by exploring not the whole slice, but only a few values. And here are our players or our actors in the game. So positions of ion at each time step, values of potential energy at each time step, increment of the potential energy of present and future time steps, gradient, and then increment of the position, which is gradient, damping parameter, and delta t squared. So if we use these little equations in the algorithmic way, one after another, and then feedback it in the rotating cycle, we expect that this will bring us to the minimum, if the minimum of the function exists. And this is different from sorting values, and this is different from what we do in calculus by finding where derivative is equal 0. And the reason for doing this algorithm instead of previous 2 options is that, as Sarah correctly told, a huge number of degrees of freedom and grid points. Okay. So before we were trying to think as natural scientists, now we need to think as programmers. There are multiple programming languages, and I think no one of us is majoring in computer science. So it's not our obligation to know computer languages. But there is a way to communicate protocols between designers of software to avoid problems of translation. Even if like two persons know different programming languages, they may pass main idea, the algorithm. And the language of flowchart diagrams is a standard tool to communicate it. So it is, you see, it's just very few words in this language, in this dictionary. So one uses the symbol of disk, symbol of like cylindrical object for data, arrow for data transmission, rectangular for math operation, and forking diamond for decision making, for branching, where there could be 2 different outputs. So basically, here is algorithm. Here are the equations that we solve, summarized in a form of an algorithm. So as an input, we use initial guess of geometry, size of a step, delta t, and tolerance. Tolerance is needed, I will say about it in like few seconds, to stop optimization and as a criterion of success. So I'm skipping this diamond and criterion of success here and there for next few seconds. So we start with initial geometry at time t naught. We compute potential at this initial geometry. We also guess an initial step. We need to make an initial guess to compute the derivative. And then we compute the next derivative, delta r tn, as derivative times delta t squared over 2. Then this increment of position is added to our present value of the position, and we rename it as a new position, r of t n plus 1. Then we compute potential at t n plus 1, and then we compare if the potential at previous step and potential at next step are close enough. In some sense, it relates to calculus way to find minima. If the potential doesn't change, it means the gradient will become 0 and it will be the minimum maximum. But here we just tell that energy change with certain amount of steps comes to saturation. If the energy change is less than a tolerance factor, then we can celebrate a success. If it is difference, if the increment of potential is bigger than tolerance factor, we are funneling all our data as a feedback to a next step. And we recompute increment of position, we change our current position, we recompute the potential, and then we make a check once again. If it is bigger than tolerance, we repeat. If it is smaller, then we celebrate success and tell that last of the computed geometries is our optimal geometry. Last of the computed energies is our optimal energy. So a patience of a human and the patience of a computer is limited. They have different orders of magnitude, but we need to take care of resources. And when in like a couple of minutes we will pretend that we are computers, we need to agree that if the algorithm doesn't give success within, let's say, 10 steps, we need to stop this game, right? We cannot work forever. And although we are short in time, I'm going to tell an anecdote. It's very old, but maybe sorry, I shouldn't laughing when telling anecdotes, but I hope that you didn't hear it before. Lola may have heard, but I think oh, Lola, please do not disclose me.
Okay.
Okay, so a programmer is working for a company and then he doesn't come for work. He doesn't come for work one day, second day, third day, and the colleagues start worrying, like, is he healthy? Is he like has a virus, or maybe he needs some help? And they made a delegation and knocked to his door. The door was not locked, it's open. They looked through the apartment and found the programmer is a little skinnier than usual, with alive, but with blue skin, shaking hand, laying in the bathtub and carrying a bottle of shampoo and reading, apply to your head, rinse, repeat. So it is what happens if we literally follow an algorithm without this breaker, without the condition for success. So in the algorithm that a programmer was following, there is no criterion to stop, criterion of success. Like if your hairs become shinier than sun, then stop the procedure. Something like that. Okay, so we are going literally to literally follow this algorithm, and we are going to apply it to a dummy problem, to an oversimplified problem where we know the solution. So our goal is not to check the solution, but to check the algorithm. So our problem is that potential is equals to elongation, the r squared quadratic potential, where the answer will be r equals 0. But by the rule of games, assume that someone can compute this function for us, but we do not know the answer. We do not know this quadratic function. We can only play a game like our helper sits in the next door, and we are sending a little piece of paper like, compute what will be the potential for elongation equals 0.1. Compute what will be the potential for elongation equals minus 0.5. And then at some point, we need to, with algorithm, arrive to a minimum. Make sense? So we will start somewhere away from the minimum and hope that through several steps, we will arrive there. So here I suggest some parameters. So initial R naught will be -5. The criterion, let's put it 0.3. Initial increment of position +1. Time increment square root of 2. It's made intentional so that t square over 2 will be equals 1. And gamma parameter, let's be 0.3. So let's go to the yes, to the form online, and just try to fill this table. So u of -5. So it will be 25. Delta u. It's too premature. We need to do one more step. Delta t is always square root of 2, so that our delta t square over 2 will be 1. And now we need to go to the next line. So step number 1. Since by initial conditions we set up, we agreed that initial increment will be +1. We'll go from -5 to -4. At -4, the potential will be 16. Now we can compute delta u. So it will be 16 new minus old. 16 minus 25 will be -9, right? Correct? Now, -9 divided by +1 will be -1, right? So it is our gradient. Time increment is the same. The delta t squared over 2 is the same. And now we compute delta r. So we have minus 0.3 times minus 9 times 1. So 3 times 9 will be 27, and we divide by 10. So it will be plus 0.27. Am I correct? No.
2.7.
2.7. Yeah, thank you for the correction.
Great.
And
Just,
then
quick question. So on the second line under negative delta u over delta r, should that be a +9 since you have negative 9 divided by 1?
yes. Okay. And then if no, but still the increment is positive, I think. Now for the step number 2, our new position will be -4 plus 2.7, right? So it will be minus 1.3.
Yeah.
Correct. And then we need to compute what will be the minus 1.3 squared. Now it becomes too complicated, and I pass calculations to you. So please take your calculators and let's try to continue together. So I will just invite you one by one as you appear on my screen. So Hadassah, would you tell, either dictate to me or type into this online form? So minus 1.3 squared.
Or 1.69.
Okay, 1.69. Yeah, thank you. The next is Hanmand. What will be the 1.69 subtract 16? Can you compute it?
Minus 14.31.
Minus
14.31.
14.31. Okay, yeah, thank you. The next in my list is Amir. Amir, would you please compose a ratio? So I think it will be minus this 14.31 divided by delta R,
2.7.
which was 2.7.
5.3.
What?
I'll do 5.3. Yeah.
Okay. Plus or minus?
Plus.
Plus.
5.3. Okay. Then dot t is the same. Dot t squared over 2 is the same. So next on my screen is Amara. So this is the hardest calculation so far. So minus 0.3 times
5.3.
5.3 times 1, right? Because our delta t squared over 2 is 1. So Amara, would you please compute?
1.59.
1.59 and
Minus,
minus
yes.
Minus get cancelled.
minus.
No,
I was sure that it is minus.
that gamma value is negative, so it may be a positive 1.59.
Yeah, the minus, it would be positive.
Plus?
Yes.
Okay, better. Okay, now let's go to the next step 3. And next in my list is on the screen is Haley. So our previous position was minus 1.3. Our increment is 1.59. So can you add together?
0.29.
Okay, 0.29. So you see, we approach quite close to 0. Okay. Now thank you, Haley. Next in my on my screen is Said. Said, what would be the 0.29 squared?
0.29.
Use calculator. It's not
Yeah.
for.
Zero 0.0841.
Huh? How many?
0.0841.
0.0841.
Mhm.
Okay. And now we need to subtract this small number minus 1.69. So
minus 1.6059.
1.6059.
6059.
Okay, and at some point we may round up because it becomes
Yes.
too many. Now let's compute the gradient. So this number over increment of position. So this number divided by 0.20 by 159. And next in my list is lower. So this number divided by this number. It should be very close to 1, right?
That in
Yes.
mind.
Pardon?
Is that minus 1.6059?
1.06?
No, I'm asking, is that minus 1.6059?
Yes. Minus 1.6059 divided by 1.59.
So 1.01.
1.01. Okay. So it was the gradient. Now same. And next in my list is Sarah. So please try to minus 0.3 times this gradient, which is 1.1, and then delta t is the same. Zero. So plus or minus?
Plus
Okay. So and then I think we are over of all class attendees. So but you see, with this smaller and smaller increments, we approach closer to minimum, and at some point it may flip the sign in the last column, and if you go too far, it will return back. So let me return back to the slides, and here are the numbers from previous years. So at very soon, at like maybe one more step, one arrives that change of the energy becomes smaller than tolerance. So basically, we are done. This is an algorithm how the computers are finding the minimum. And at home, please try to repeat the same exercise for different initial parameters for different dt, which is like square root of 3/2. Okay, meeting is done. Many thanks for your questions. I think I'm 6 minutes over. You may need to go to other meetings, but I'll stay here a